Here we have a mechanism, a 4-bar mechanism. This is a slider crank mechanism. This is the crank link, or C is the crank link, and then there's this coupler link, CA, and there's this slider which moves back and forth along this horizontal direction. We have a revolute joint at point O, another revolute joint at point C, another revolute joint at point B, and then there's this linear action. We have this force acting relative to the coupler link by 90 degrees, so it is always at 90 degrees orientation with respect to this link. And the linkage starts its motion when it is aligned along this horizontal line. So there's our coupler link, crank, then coupler at point B, and then point A, and here we have our force P applied to this linkage, initial condition. And in the final condition, initial condition where theta is equal to 180 degrees, this is the theta angle between the crank and the coupler. And in the final case, theta is equal to 0. That means the crank and the coupler will be on top of each other in the final case. They'll be aligned in a situation something like this. There's going to be our point A, there's point C in the final case. Now, what the question asks us is about the angular velocity of this bar, the coupler link, when it reaches theta equals 0 degrees, and it starts its motion from rest. So in this condition, it has 0 motion, then a force is applied until the end, and then we are asked to find out the angular velocity. If we are to find out the angular velocity of this is an absolute measurement. Remember, the angular velocity is an absolute measurement, so we need to measure it relative to some inertial frame or the axis. We can measure it with respect to this horizontal axis, or here we have an isosceles triangle with link lengths B and B. If I can draw a vertical line here, okay, this is vertical, then the angle here will be theta over 2, and this theta over 2 angle will be changing throughout this motion. And it is measured with respect to the vertical line, so it's an absolute measurement. By making use of this theta over 2 measurement, I can actually find out the absolute angular velocity. So let's keep that in mind. The other concern that we should have here is finding the energy, the work done by this P force, and as a result of that, we might be able to write out the energy equations. Now, if we consider this link as a uniform link and mass center at B in that case, the mass center's location in the vertical direction will not change. That means we can neglect the potential energy part. There's no elastic material here. That means we can neglect the potential energy due to elasticity. The only thing changing here is the existence of this non-conservative force P and then the kinetic energy. So we can write out an equation relating these two. As a result of the work done by this non-conservative force, the kinetic energy of the bar or the coupler link will change. The concern that we have here, I was speaking about that, is that this P force is always 90 degrees relative to this link, but when we try to calculate the work done by this P force, then we need to calculate the displacement as a result of this P force, and the displacement of this point A is changing throughout the course of this motion. It's not a circular track, it's just a general plane motion that it does. This coupler does a general plane motion, and it's quite hard to do this measurement. However, we can use something else, some other information, because a point here about this link has only a motion in the x direction, and this is in the horizontal direction motion of point B. Now, this horizontal motion of point B can be used but then I need to move this force to point P. And this is some knowledge that you should already have from your statics course. If I move this force at point P, then there should be a moment associated with it due to the moment formed as this force is applied at point P. And this moment, in that sense, will be in the clockwise direction, and its magnitude will be P times B. That's the moment that is applied if we move this P point to B. It will be related to the force and the moment at point B. Now, in that case, now only thing left here is to find out the component of this P force. And the component of this P force will be found out by this theta over 2 angle. If this is theta over 2, then this angle is theta over 2. It's not able to show, but yes, there we go, theta over 2. Then the force here is P times cosine theta over 2. And theta over 2 will be changing as a function of time. And this is going to be changing as a function of time. But then there's also something that is related to theta over 2 that will change as a function of time. And that's the OB distance. I can relate that distance as this vector x, or the axis along the axis of x. And this x can be calculated conveniently by using this b and theta over 2 functions. Here, x will be calculated by using b times sine theta over 2 will give me this length, and 2 times of that will be the x distance. So now I have this x times p cosine theta over 2, and x is defined in terms of theta over 2 as well. So now it's time to calculate the total work done by the non-conservative forces. Here's our total work done by the non-conservative forces. Moment and the direction of motion of this link is in the same direction. The link starts its motion from this location and then rotates in the clockwise direction. From 0 angle, it will move to this location where it has moved a total of 90 degrees or pi over 2. And the direction of motion of this link and the moment are in the same direction. So the work done by this moment is a positive work. So that's why we have m times pi over 2. Or you can calculate it in this respect, because m is in the clockwise direction. Due to our right-hand rule, it's a negative direction. Then we can use it as from negative, and theta is from pi to 0 degrees. And you'll see that we are consistent with our assumption here, where we calculate the total work done by this non-conservative moment. M has m times pi over 2. The other term here is about the force, non-conservative force. This is our force direction, the component of P force along the horizontal. And then, although force is to the left, x is defined, the displacement is defined to the right in our calculations. Therefore, we have a minus sign due to the opposite direction of the force and displacement. And we already said that this x can be calculated as a function of theta. And then if we take the differentiation of this x as dx, then saying theta is the only term as a function of time with a function of time, then we get this term as b cosine theta over 2 d theta. B is constant, so it's not a function of time. It's not going to appear in this equation as dB. And as a result of that, we calculated the total work done by the non-conservative forces. Now, the next thing to work on is the kinetic energy. And for kinetic energy, we have to determine the velocity information of this system. We need to determine the velocity of the mass center, which is located at point P. So I need to find out what V is. And also omega. And omega is something that I'm also looking for, which is something to be determined and asked in this question. Now, V and omega, are they related to each other? They are related to each other by the instantaneous center of zero velocity. This is true for any rigid body. Velocity and omega will be related to each other if you can use this instantaneous center of zero velocity. The good news is that at the beginning of the motion, velocity and omega, the linear velocity and angular velocity, are equal to zero. We are starting from rest. In the final condition, if we can find out the instantaneous center of zero velocity, then V and omega will be related to each other, which will give us a single unknown, because the energy equation that we're going to derive is a single equation. We can only determine a single unknown from that equation. That's why I'm trying to relate this V and omega. And instantaneous center of zero velocity for this coupler link can be found actually because we already know the C point of this coupler is doing a circular motion due to the motion of this crank. And then its velocity will be in the perpendicular direction, and perpendicular to its velocity vector, we can draw a line here, and then perpendicular to the motion of this B point, which is always in the horizontal, it means we have a vertical line, we can draw a line, and this point will be instantaneous center of zero velocity. So at any instant, actually I can calculate that. And in the final instant, this instantaneous center of zero velocity will be located as B away from this point. And as it is going to be appearing B away from this point always, then the velocity of the mass center will be calculated as 2 times B. This is B distance, this is B distance, and this is the mass center at point B. 2 times B omega. And how I could tell this, because at any instant of this motion, the instantaneous center of zero velocity is always 2b away from point O, or b away from point C, in other words, at any point. This is an arbitrary point, and still we have this instantaneous center of zero velocity to be b away from this point. And you can do this calculation by using the trigonometry again, and then find out that this is actually theta over 2, and then this angle is theta over 2, and we will be able to calculate that this is an isosceles triangle, and this is if this is B, then this has to be B as well, and instantaneous center of zero velocity will be always B away from C point. So at its final condition, it is B away from the C point, and then the mass center of this link is 2B away of this instantaneous center of zero velocity. Therefore, velocity of the mass center at this final instant will be found by 2B times omega. And if we write out the kinetic energy equation, there's mvg squared, and then we have ig times omega, and the thin rod, if you remember, it is 1 over 12 ml squared. L in this case is equal to 2b, the length of this coupler, and this is the resultant kinetic energy term. Relate this kinetic energy term to the work done by the non-conservative forces, and we are able to calculate the angular velocity of the coupler link.